yourselves. Okay. So YouTube link.
Good night.
Okay, good morning, everybody.
Good morning.
Awesome.
Good morning, ma.
Good morning, ma.
And welcome to another class.
Good morning, ma.
Good morning, ma.
Good morning.
Okay.
Good morning, ma.
Okay, so I'm going to be teaching you.
Good morning, ma. Good morning, ma.
You don't do this greeting now.
Okay, can we all
Good morning.
can we concentrate on the class now? We are already behind schedule. More participants, mute on. Okay, so we are all going to be in this section. I'm going to be taking you through the concepts in thermochemistry. So we'll talk about first law of thermodynamics, and we'll also talk about spontaneity, that's entropy, and free energy. So let's quickly begin with thermochemistry. What is scope? Okay, this is the scope of what we're going to discuss. And also this is the first part of our discussion. And the second part will be on the second slide. So let's start. Some things that you're familiar with: energy is the capacity to do work and transfer heat, or to produce heat. It can occur in different forms, but all these forms can be summed up to potential energy and kinetic energy. So we can look at heat energy, mechanical energy, chemical energy, and all forms. The aim of thermodynamics is to study how this energy changes from one form to another, simply because we know that we cannot create energy, but we can change it. In this universe that we're in, we can change it and use it for the purpose that we desire. Thermochemistry is a branch of thermodynamics that studies heat changes in form of heat, especially when we're dealing with chemical reactions. It's associated with chemical reactions. Like in all everything that you want to deal with, you want to have some basic definitions so that you understand any concept that might be discussed around it. So one of the basic things that thermodynamics and thermochemistry, which is its branch, talks about is what a system is. Anything that you are trying to study is what thermodynamics calls a system. In the concept of a chemical lab, this is a beaker. Inside this beaker is a solution of barium hydroxide and ammonium nitrate. The solution of the barium hydroxide and the ammonium nitrate is the system that we are studying. Any other thing in its immediate environment is called the surrounding. Everything outside it is called the surrounding or the environment, or in some other climes, the reservoir, because that is where we're looking at energy, because you can exchange energy with your surrounding, which means that you can dump energy there and you can take back the energy. Both the system and the surrounding make up what we call the universe. So the universe will be the totality of all things. The system is separated from the surroundings. So this is our system. It's separated from the surroundings. This is the boundary of our system here. Unless we are trying to study the gas evolved, then that would be the system. So the system is separated from the surrounding by what we call a boundary. Now, the nature of the boundary is important because it can make the system isolated, it can make the system closed, it can make the system open. In an isolated system, the system does not exchange anything with its surrounding, so it is closed out to the surrounding. An example of such is a gas that you put in a cylinder, or that you put a tea inside a very, very insulated flask. Gradually, energy may be released in form of heat, but in an ideal system where you don't allow even heat to be exchanged, it's an isolated system, meaning that in the space of time that it does not go into the system, it is an isolated system. So, isolated system does not allow exchange of energy and matter. A closed system can exchange energy, but it cannot exchange matter. Matter, anything that occupies space and has mass. So an example of your closed system, okay, an example is given there, a radiator engine. Another example would be a pot that you covered up. You have water in it, you cover it up, you do not allow any steam to come out, or you can heat up the pot, you can freeze it. So we have a lot of closed system around us. In your radiator engine that is sitting there, the sun can heat it up, but since your fluid is not coming out of the system, it is a closed system. So closed systems are bound all over the place. The most common, or the commonest one, whichever one English permits, is the open system, where you can allow both energy and matter. It is the commonest and also the most complex of all of them. So that means that the boundary of the open system is porous. Okay, so let's do a little bit of justice to the word energy in itself, since that's what we are studying in thermodynamics. Generally, like defined before in the introductory slide, it is the capacity to do work. So the energy of a system is a sum of its kinetic and potential energy. The kinetic energy is energy as a result of any motion that the system is undergoing, any kind of motion, rotational motion, translational motion, that's motion in a straight line or motion in a angular manner. It's called kinetic energy. And that kinetic energy depends on the mass and velocity of the object. So two objects of different masses, even if they are moving at the same speed, so it depends on that. Even if they are moving at the same speed, the kinetic energy will be different as long as their masses are different. That's why at times you see a smaller object just propelling faster at a certain time. Usually in so that's something in motion. Kinetic energy of atoms is characterized by their constant motion. So one other thing about kinetic energy is that it's a result of temperature or thermal energy. Motion gives rise to heat. So objects in motion will produce heat, much like charged particles produce magnetism. When they are in motion, they produce magnetism. The potential energy, on the other hand, is energy as a result of the position of the object relative to another. So you can talk about gravitational potential, you can talk about electric potential. So this is the potential energy of this mass relative to this position. That's the gravitational potential. Is called is given the mathematical formula mgh. Again, it also depends on the mass for this one. You can have potential energy between two charges, and then you call that electrostatic potential energy. That electrostatic potential energy is very important in chemistry. Why? Because everything is made up of electrons, and electrons are charged particles. Other than that, electrons are in the potential field of the nucleus. So there are several nuclei in the molecule. There are several electrons. So there are several potentials that are taking place. But there are several types of potential energy as a result of the electrostatics going on in a molecule. Okay, so arise as interaction of a potential charge between particles. So the greater the electrostatic potential, then you know that the charges are close by. Another form of energy that people usually talk about is the radiant energy, because it is from the sun. Nowadays, everybody talks about going solar because it's green energy. It's like an unlimited source of energy. You can convert that radiant source of energy to almost anything. Our plants convert it to energy for the processes that takes place in their system, and we use up that energy. Like I said before, the chemical energy, the most important ones, is stored within the molecule as a result of the structural arrangement between the electrons and the nuclei. In chemical reactions, this energy can be used to convert substances to a completely new substance. So that's why energy is important. The major units of energy that we come across, this is this SI unit, joules. The oldest form of units being used for energy is the calorie. And I'm sure that we still see it a lot nowadays, especially in food chemistry. Another form of unit Another form of unit that we constantly see is the electron volt. So this is when you're dealing with electrostatics. Okay, so some quick examples on units on energy. These are familiar concepts, but we'll still talk about them. So some useful concepts. Some examples. A person weighing 75 kilograms runs 1.78. What is the person's kinetic energy? It is important that when you have a question, you write out your parameters. So what is given in the question is the mass and the velocity. So we write it out. And we are told to calculate the kinetic energy. The kinetic energy is given this formula. In the previous slide, I wrote kinetic energy as T. That is another form, another conventional form in which kinetic energy is presented. Potential energy is presented as V. So what do we get? Putting our values, mass 75, velocity 1.78, and pressing in the calculator, we should arrive at energy being 119 joules. So the answer has been given to 3 significant figures. We have this in 3 significant figures. We have that in 3 significant figures. Another example that is presented to us. What is the potential energy of an automobile 1360 kilograms parked on the top level of a parking garage? So looking at this, we know that we're dealing with a gravitational field, and the potential energy in a gravitational field is given as mgh. From the question, mass, gravity, acceleration due to gravity is a constant, and we are given the height as the 36.6. So if we slot in all these values in the formula mgh and press and do the calculation, we get 488,103, a very huge number, which we can approximate with the kilojoules, the suffix for all units. It makes your energy units more compact. The last example that I want to work before we move on and talk about other basic concepts in thermodynamics and thermochemistry. So we're given the question, find the distance between 2 spheres of charges, charge 1 and charge 2 respectively, if the electrostatic potential is given by that. Again, let's write out what we need. You have a question?
Yes, ma'am.
Please go ahead.
Ma, that G that you gave us to be 9.806. Can we also use 9.8 or use it in full?
So usually, if I'm to answer, if you're trying to be very accurate, it is better to use the longer version. Now, if you're in an exam hall, usually the constants are given at the beginning of the question. You see it's close to the instruction. So it is important that if your examiner gives you a value, use that value, especially when you're doing MCQ.
Okay, ma'am.
All right.
Thank you.
So, and that applies to not just here, but it applies generally to almost everything that you do. Okay, so moving on. If the electrostatic, sorry, that's the question. So as before, it is important to write out everything from the question. So we are told to calculate the distance. We're given electrostatic potential energy, which we have written as EL, energy due to electrostatic potential, is given as this formula. K is a constant of proportionality with the value. So K is 8.99 times 10 to 9. So Q1, charge 1, and Q2, charge 2. So we are told to find R, meaning that we are going to make R the subject of the formula. Okay, so I've written everything out. So energy is minus 450 joules. So making R the subject of the formula will be K times Q1 times Q2 over E electronic energy. Okay, so distance here is also R. Please, let's take note of that. So if you make it the subject of the formula, you get that. So we said that K is a constant. Charge 1, 0.03, charge 2, 0.01. So we get the distance between them to be 0.599 meters. Just to add more light to the question asked previously, when you're dealing with significant figures, it also matters to how much significant figures you are given. So all that you need to put into consideration. Okay. More on basic concepts that we use in thermodynamics and thermochemistry. Work. We defined energy as the capacity to do work or transfer heat. What is work? Work is energy used to cause an object to move through a distance against a force. This is a very simple definition. So any energy that you exert that causes a displacement in an object, that is work. If it's something that you lift a cup, you compress a gas, you have done work. If somebody pushes you, somebody has done work on you. So as long as there's a displacement, that is, the object moves through a distance because of a force, work has been done. In chemistry, there are several types of work. There's surface tension work, there's height times distance work. But in chemistry, the work that we are concerned mainly about is called pressure volume work. So pressure is the force, V is the displacement. So when you apply pressure to gas, it causes a displacement, whether it's in expansion or in compression. So this is the general definition for work. So the negative sign in the sense that we have the work has been defined by the system. So work is defined as the amount of energy expended by the system to cause a displacement to an object. So the general convention for work is work positive. So work done on the system. Remember, system is part of the universe that we are interested in. You can talk about negative work. That is work done by the system. So that's negative. That's the sign convention. So by definition, in when you're dealing in thermodynamics, you say that the work done is because we are saying work done by the system. So which means it may end up being positive depending on the net displacement. Displacement is a vector quantity, meaning that it has direction. So P is the pressure acting on the system. That's the force that you're working against. Then the other form of energy, so energy capacity to do work or transfer. What is heat? The other form of energy, heat. So that's the energy that causes a change in temperature of a system. So it flows in and out of this system as a result of a temperature difference. So anytime that you transfer energy from the surroundings through the boundary to the system, you have done work in terms of heat transfer. So that's why heat is defined as a transfer of thermal energy between two bodies that are at different temperatures. It flows from it, which makes sense. There's energy always flows from a high energy to a lower energy unless a force is applied that pushes it the other way around. It flows from a region of higher temperature to one of lower temperature until there is a thermal equilibrium. And at thermal equilibrium, their temperatures are equal, and then there is no more heat flow. When the temperatures are equal, we say that they have reached thermal equilibrium. Both work and energy are forms of work and heat are forms of energy. And since they are forms of energy, they have the same units as energy. So joules, calories, electron volts, and so on and so forth. All the forms of energy units that you can talk about. It is convention to define the heat capacity of a system. That is how much heat energy a system can transfer out or can accept. This heat capacity, the concept of heat capacity is very, very important in designing new material. I remember the last time that I was trying to buy a pot, and in one of the research that I did, you have to look at metals that can make your heat uniform so that the food doesn't burn easily. So that is looking at the heat capacity of the concept of the system. And that heat capacity, it's even for those people in engineering that design engines for different things, especially the ones that are working at high temperatures, you want something that can withstand heat. So it needs a high heat capacity. So it's a very useful concept in designing new materials. So you see people in such research that are trying to add some materials that can help the heat transfer a lot. Okay, so back to our chemistry. The heat capacity of a substance is defined as the amount of heat required to raise the mass of a substance by 1 degree Celsius. Since 1 degree Celsius and 1 Kelvin are the same, so occasionally you can see 1 Kelvin by 1 Kelvin. 1 degree Celsius, degree Celsius has been an old unit that has been used for temperature. The heat capacity is often given the symbol Q. In some other text that you may use, we have Q. Okay, I'm going to write the name of the textbook. So, sorry, Its capacity, it is given the symbol Q. Sorry, not its capacity. This is heat. I'm not sure I wrote it in the last slide. And work is given W. Its capacity, on the other hand, is given the symbol C. Because it's required to raise the temperature by 1 degree centigrade. So this is the unit is joules per Kelvin or joules per centigrade per degree centigrade. We can also talk about the specific heat capacity of a substance. It is the amount required to raise 1 gram of that substance through 1 degrees centigrade. So it's given the symbol CS to indicate that we are being specific. Through 1 Kelvin of a mass of 1 gram. And because of that, the unit is joules per, the unit of mass per Kelvin, per unit of the temperature. A common heat capacity that we encounter in chemistry is the molar heat capacity. We are looking at the amount of heat required to raise 1 mole of a substance through 1 degree Celsius. So it is given the symbol Cm because we are saying molar heat capacity. So it's Q divided by the number of moles divided by the change in temperature. Okay. 950. Any question for now? Let me see.
Yes, ma'am.
Online. Okay. Go on, please.
Okay, ma, see, you said and this heat capacity, how is that put it? The unit for this temperature is degree Celsius. When we are solving, can we use like standard temperature, which is 273 Kelvin, to convert?
If I understand your question, what you are trying to say is that can you use Kelvin?
Yes, ma'am. Like you want
So
to.
let's look at. Do I have an example here? I'm not sure. Okay, I have an example there. I hope we'll be able to get you. But to answer your question, before the example, what is the conversion between? Let me throw it back at you. What's the conversion between the degree Celsius and Kelvin?
That's 273, ma'am.
Yeah, so what is it? What is it? You need to, it's not just 273. What's that relationship? So one degree Celsius
1
is equal to
Celsius
what?
goes to 73 Kelvin.
3 Kelvin.
273 Kelvin.
Yes, ma'am.
Is that what you're saying? Okay, so are you sure?
Yes, ma'am.
Okay, so what is 10 degrees Celsius?
That will be 273 times 10. So that's 2730 Kelvin.
Okay, so you can see that you are. So please, can somebody tell me what's the conversion between Celsius? Because that is wrong.
C plus 73, ma'am.
Say that again.
C plus 73
Kelvin
plus
plus 73.
See?
plus
Yes.
plus 273.
So whatever your
plus
temperature is,
273
plus 273.
Degrees Celsius plus
Celsius
273.
plus 273.1. What's that?
okay, so we can switch off we can mute our mics. Thank you. So the conversion between Celsius and Kelvin is whatever you have. Kelvin is Celsius plus 273.15. Whatever you're looking at. So if you're given 10 degrees centigrade, your Kelvin will be what your temperature in Kelvin will be 273 plus 10 degrees centigrade. That is the conversion. So now back to your questions. There are some cases where it is needed because you might be dividing by temperature. But here, because you are looking at the change in temperature, whether you convert it to degrees centigrade or not, your answer will be the same. So like I was saying, there's an example, they're almost at 10. Let's quickly look at one of them. Yeah, so this is an example on work. Calculate the work associated with the expansion of a gas from 46. So we're looking at work done from V1 is 46 liters to V2 64 liters at a pressure working against a pressure of 15 atmosphere. So whether you are told or not, a very good practice is to convert your unit to the SI unit. So it is meter cube for volume, and it is Newton per meter, which is Pascal for pressure. More often than not, those conversion units are given at the beginning of your question. Okay.
Sorry, my meter cube or centimeter cube?
No, the SI unit is meter cube. So this is bracket that I wrote here, not cm. The standard unit for volume is meter cube. You know, the standard unit for length is meters. And that's the fundamental that you get it from. So, okay. Unless the only time that you don't need to do that is if your question specifically requires it. Okay, so let's quickly work
Excuse
this.
me.
Yes, sir.
Ma, I think the unit was supposed to be Newton per meter square.
Sorry, yes, Newton per meter squared. Sorry. Yeah, correct.
Sorry, ma, please, may I ask a question?
Yes.
Please, ma, this pressure volume work you gave us, where you said W equals to minus P delta V. Ma, when we solve a question, can there be a situation whereby the answer we get is positive?
Sure. So that was what I was trying to say the other time. There's one example here. I don't think we'll get to it today because time is against us now. I don't know. But see, let me explain that further. So how is work defined? Conventionally, work is defined is when you're defining it with respect to a system. So you define work as work done by the system. Why are you defining it with respect to the system? Because the system is what you're interested in. So when you are referring to work, you are always looking at the work done by the system. System is the place of interest. So you are not it's not like you're not interested in the surrounding, but what you're interested in, what the thing you're interested in, what you want to learn is not what you're not interested in, what somebody else wants to learn. So everything will be with respect to the system. So the convention is that if the system does work, it will lose energy. That means it will be negative. So system does work. If the surrounding is the one that is doing work on the system will increase in energy, and you say it is positive. That means that work done on the system. So when the general definition of that work that you want to work with, it will be the work that the system does. Now, if in the process, the work that you're looking at, like for example here, the volume decreases. So you see, this is an expansion work. If it's a compression work, in the long run, your answer will be positive, and it will tally with the fact that it's the system that is the surrounding that is doing work on the system. Did I was that clear enough?
Yes, ma'am.
Okay, thank you. So you have a class right now, Abby, after this.
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Okay, let's just quickly walk this example and then we'll continue with the other examples next class.
Class is actually on now. Good morning, ma.
So should I work this one or should I stop?
Ma,
Now,
just
now,
But let's finish this.
Wait,
Work it
please.
on let's finish.
man, let's work
We
it.
have
Let's
another class
Ma,
now.
just work it and let's finish it in the day.
Let's
See,
finish this.
Man, like,
let me quickly work this one. It's just 2 more lines. The pressure is 15 atmosphere, and I have multiplied it by this constant to convert it to Pascal. Volume is 46 liters, the initial volume and the final volume. So our work done is minus 15 times, this is the pressure, delta V, 64 minus V. So I have also converted it to meter cubed here because that's the conversion unit. And then we arrive at the work done. So negative. There's a negative sign here. So I'm going to share
No, man.
the slides with you. So for the sake of the class that I've started, we'll start here today. Please, you can, next class, that's Friday, we'll bring in your questions and we'll, for clarification.
Please share the recording too as well.
Chabi, you are chasing me away and you are looking for recording too.
No, sorry, ma, we're not. Sorry.
No, ma'am, we are not chasing you away.
wow.
See you next class. Yeah, did I record? Well, it's on YouTube.